So good afternoon, everyone. This is Oscar Salgado from Netherlands. And today we continue with our round of webinars. This time the webinar that will be presented today in ZDZW is focused on 3D multi-camera system for non-destructive visual inspection with a 360-degree view. Will be presented by our visual inspection experts from ITA, Adrián Cervera and Nuria Heredia. So without further delay, I give the floor to Adrián, who will impart this webinar. So thank you, Adrián, and the floor is yours.
Thank you. So, okay, as Oscar said, this webinar will be presented by my colleague Nuria. She worked with me in the industrial inspection systems at ITI. She's our AI researcher and also software developer, and she will explain the second part of this webinar, and the first part is being presented by me, and I work with him and the rest of with her and the rest of the team at the Vision Systems department as engineer manager. So as the first slide says, we have been working in non-destructive inspection services for digital enhanced zero waste manufacturing, and today we are going to talk about our system. And the title is 3D multi-camera system for non-destructive visual inspection with 360-degree view. So here we have a small index of the presentation, the zero defects, zero waste introduction, to talk a little bit of the project, also some information about ET. Then we will talk about our hardware, how our multi-camera system works, and the object reconstruction algorithms. And then Nuria will show you the analysis algorithms and some use cases and applications. Okay. Okay, the first point is to know why zero defects, zero waste it's important, and well, as you know, the focus of this project is to address some problems that we have detected in manufacturing process, and that are mainly related with waste management. So the idea is to reduce this amount of waste, and this is also aligned to reduce cost, to reduce the complexity of the systems that perform this kind of tasks, and also to reduce the complexity to integrate these systems in industrial inspection lines. Okay. As an overview, taking into account this kind of improvements, we have been working to create a non-destructive inspection technologies, mainly for three reasons. The first reason is to improve this production efficiency. Second one, it's to reduce the number of defects that we had in production lines, and all of this is aligned to achieve more eco-friendly manufacturing, and also to reduce the carbon footprint in the processes. So we have been working mainly in two tasks that are related with visual inspection and also volumetric inspection. Visual inspection to detect defects on the surface finish of these parts, and volumetric inspection that is related to detect defects on the shape of these pieces. And regarding the pilot, we have been collaborating with GLN in order to develop and apply all these advantages and ensure that they are working well. Now, some information about ITI. ITI is a Information and Communications Technology Research Center based here in Valencia, in Spain, with more than 30 years of experience. And we work with different universities and also private companies to solve different kind of challenges. And well, we have different lines of research and development to address all these kind of problems. We work in artificial intelligence. In fact, our department is located there, and our objective is to improve companies to help companies to improve their processes. We have also lines in cloud computing, cyber connectivity and cybersecurity, big data analytics, human-computer iteration, and so on. We are more than 300 people working in ITI. We have more than 150 projects annually with private and public entities, and more than 400 customers. Now, I'm going to introduce you a little bit some problems of the non-destructive inspection systems. The most common that are used in these days are mainly 2D and 2.5D cameras to take some pictures of these parts, but mainly 1B or view from the top or in some concrete positions of these parts. We have also some 3D scanners using different kind of technologies like stereoscopy, structural light, etc. The problem of these systems is that they are very slow in their reconstruction process, and there are also something that it's called multi-view systems, but more or less the difference with a 2D is that they took several pictures in different positions, but this has some limitations that are listed here. The problem is that they require support or handling with this part. Usually they use robots or conveyors to move these parts. The result of this support or conveyors is that we have hidden areas where we don't have the ability to check the parts or to run the analysis. So we have less information on this part. And as I talked before, also 3D scanners are very slow, so usually it's not possible to work in line with this kind of systems, and also lighting and shadow problems, that it's a common problem in the industrial vision systems. So here is where our solution starts. Our idea is to solve all these problems with a complete system that try to address all of them. We use a multi-camera device. We used to work with 16 cameras because it's a good distribution between cost and results, but the system can be configured and used from 1 to any amount of cameras, depending on the requirements of the precision and also the customer requirements. The most important part here is that we capture the piece in flight. That means that we take the picture when the piece is in the center of all these cameras, so we don't have any kind of occlusion, and we can assure the quality of the whole piece. And we have also worked very hard to achieve a good lighting system with diffuse panels that ensure that the light inside of this acquisition system is very regular, and we don't have any kind of shiny surfaces or shadows. So the benefits are clear, as we take the captures when the piece is flying. We don't have any kind of occlusions, and we can ensure the 360 degrees quality of every single part. Also, this has an impact on integration cost, because we can reduce integration cost because we don't need any ad hoc system to position the part put inside the system. In fact, it's even possible to capture different kind of parts mixed. So it's also a great advantage. And also, to take all the pictures at the same time enables us to work in line in real time to ensure the quality of the whole production, and avoid another methods to ensure quality, like sampling, where only a part of the production is reviewed to more or less ensure the quality of the whole production. Well, here I have a small video to show you how the part is captured when it's flying, but it's small and you can see it. But well, the concept is this black area is the PCB lighting system, and when the part is in the middle, we launch the 60 camera triggers simultaneously, and with these pictures we reconstruct the object and can apply different kind of analysis that Nuria will explain in a few minutes. And this table is more or less a summary of all the things that we have talked previously. In industrial inspection systems, we have more or less some common problems. For example, that they can't guarantee the quality because of occlusions or human error, because sometimes they don't use any kind of machine. It's the quality is reviewed by humans, and it's impossible to ensure any kind of repeatability or accuracy in this process. Or sometimes they use sampling inspection, that it's also a problem. So in other side, with our technology, we can check the whole inspection working in line. We can check the full all the parts of these pieces, so we can ensure a 100% quality. Another problem of the other system is production times, related with the number of captures that they need to ensure different critical points, or the method that they use to make a 3D reconstruction. So using our system, that it's contactless, we run the 60 cameras at the same time. We have more speed and more performance. And another strong point of our technology is that, as we don't need to position the part at the input, the acquisition prices and the integration costs are lower compared with other kind of solutions that need that the part is always presented in the same position, or even use a robot to put the part in different positions in front of the cameras. And here it's a small video where we show how to we have mounted our prototype in our pilot in GLEN facility. We have developed a new machine that it's divided in two parts. The upper part, as you can see in this video, is the acquisition system, where it's located the cameras, backlighting, and also the optics, and at the bottom of this system we have the electrical panel, also the for the part, which holds everything, or the computing system, for example. And okay, I think that regarding the hardware, it's everything. Now it's time to Nuria to show you our algorithms.
Okay, so I'm going to share my screen.
Yeah, I have stopped to show. Yeah, it's great.
Okay, can you see my screen?
Yes.
Okay, so following up with 3D reconstruction and alignment, once we have captured an object and we have these 16 images, we can use this to reconstruct a 3D model of the part. This is done by the combination of the silhouettes through a kind of perspective cuts into the reconstruction. And this, along with a process of spatial calibration, allows us to approximate the object's shape and size. So as we can see here, these are the 16 images of this example object. And from the silhouettes of these 16 images, we construct the 3D reconstruction on the left. And once we have the 3D reconstruction, we have to align our object with the part's reference. So to do this, we first compute a pre-alignment using PCA to place the reconstruction on the reference. And then with ICP, we orient this 3D object so it is on the same position as the reference. This is because once we have our object aligned with the reference, we can compare these two. So it is possible to measure lags or excesses of material in the piece. And this process can also detect any formations such as cracks, bursts, material displacement. And this process is also tuned to very specific to the specific piece. So we can set different thresholds and sensitivities for each type of analysis. So for lags of volume or excess of volumes. So as we can see here in the image, we have a part that has a lack of material that is represented in blue on the reference of the piece. And the bottom part is a deformed piece. So it has a lack of material on one side and then an extra volume on the other. Now for more inspection algorithms that we use, we have the GD&T inspection, which analyzes the 3D point cloud that we obtain from the silhouettes of the images. And this is used to evaluate the geometric and dimensional correctness of the part. This analysis allows us to apply a wide variety of measurements and analyses, so we can detect any shape deviations and verify the specified dimensions and the tolerance of the piece. So here, for example, we have our reconstruction from before. We have it in green, and then the point cloud that is obtained from the silhouettes is represented in red. And the image on the right is the specific measurements that we conduct using GD&T for this piece. And taking advantage of this GD&T method, we can apply further analysis, as it also has the reference points. A kind of volumetric analysis by zones and with different configurations can be configured for a part. So for example, we can conduct volumetric analysis only on the top of the screw, for example. And as this method also has the texture information of each point, we can also perform surface inspection, such as one we can see on this image. Here we are detecting points that differ in color from the black that we are looking for on the screw. And continuing with surface inspection, the process with which we use to analyze the texture of the piece is divided in two phases. So first, we train the model for the part with a collection of defect-free parts, through which we learn the average correct texture of each point from the different views. And the symmetry of the piece can also be configured for this training process. So we can multiply the available points for each texture patch, and it allows us to use less okay parts to train the model. So then when a new part is captured and analyzed, the texture of each point is compared with the previously learned information to detect any irregularities. So what is the difference between this algorithm and the previous GD&T color inspection? Basically, this method detects any irregularities and deviations from the expected texture of the piece, while the previous GD&T method is configured for concrete types of texture defects, such as lags or excess of different color materials that are injected into the piece, or burns, discolorations, etc. So this allows for additional data to be collected from these defects, such as the percentage of appearance. And then continuing with other types of analysis, the SSM algorithm is a shape analysis method that was developed for pieces that allow for shape deviations, such as pieces with elastic materials or specified tolerances that are not considered a defect. And this algorithm is, same as before, also divided in two phases. First, in the training stage, the model learns the variability of the piece by analyzing multiple valid parts, which builds a statistical shape model with mean and covariance for the point cloud that we obtain from the silhouettes. And then once a new piece enters the system, its reconstruction will be aligned with this learned model, and possible deviations will be detected using the Mahalanobis distance. So here in the image on the right, for example, we can see a representation of this statistical shape model. And on the red, you can see the part of the piece that can deviate from part to part. And on the left, you can see a result from this SSM algorithm. So in red, you can see the shaped defects that have been detected. And here we have a video of what the user would be seeing when using the zero gravity. Okay, now the pieces are going through the system, so they are being captured and queued into processing. And once a piece is processed, it is added to this live data chart, so you can see the classification of each piece that it's going through the system. So in this case, it's all bottle stoppers. And also the results for each piece, for each type of analysis that we are conducting. In this case, the SSM is deactivated, and we have volumetric, surface, and GD&T inspections. And also we can see the percentage of the batch of defective and non-defective pieces. We can also see more information about the system, like any possible errors that are occurring, the percentage of defects that the whole batch presents, also classification of parts, so if any other type of part were to fall through the system. Also system information like calibration error, and we can see also the measures of each piece. So in this case, for the bottle stopper, we have the bottom and top diameters, the height of the piece, and we can see it represented on a line chart. So it is more easy to understand the batch statistics for the user. Now, here on the part inspection window, we can see in detail every analysis of each part. So we have the 16 images of the object, so we can see it more directly. Also the backgrounds that have been used, the different analyses that have been conducted. So in this case, volumetric, surface, and GD&T, and every measure in the GD&T of the results. Also, we have in the 3D view, we have every reconstruction. So we have the reconstruction of the piece, its reference, and also the point cloud. And we have also the texture of the piece, and any errors that have been detected will also be represented on this reconstruction. So here, this part, for example, as you can see, has a texture defect. So now we can see when this when this part falls through the machine and this texture defect is detected. This has also failed its volumetric and GD&T inspection, so it has more than one defect. And we can see in the 3D view that in the point cloud, you can see that the piece is kind of bigger than the reference. In this case, the reference is what we are seeing inside this point cloud. And on the surface error, you can see there in red, that is the defect that has been found for this piece. So for more examples, here we have a piece that has a break in the middle. And this kind of defect can be detected by more than one analysis. So this is going to be detected by volumetric, surface, and GD&T. analysis. We can see there is extra volume found, and also this is the representation of the texture defect that this break represents. And on the point cloud, we can see the piece is also deformed. Now, one last example. This piece is also fails the volumetric and GD&T analysis. It is let's see. The height measure exceeds our tolerance, so we can see it on the point cloud that the expected height does not match with what we have found on the 3D reconstruction. Okay, so now image-based AI models have also been used along with zero-gravity 3D to solve concrete inspection challenges. So this type of inspection allows us to tailor the machine to very specific cases and manners of capture. So, for example, on the image on the left, we have captured it through X-rays, and we have trained a supervised learning models to detect these types of defects. And on the right image also, it is a supervised learning model that we have used to train a model to detect any type of defect on a leather surface. Now, regarding industrial applications of zero gravity, the machine has been tested with a wide variety of parts from different sectors and companies, and it has proven to be incredibly versatile across many materials, shapes, and sizes. And it has also been successfully implemented in multiple production lines. As you can see here, many types of pieces that we have tested with zero gravity, even teeth. And here is the instance of zero gravity that we saw a video of its assembly before. And one of the main advantages of zero gravity is that using its core technology and with a few hardware adaptations, very different industrial inspection problems can be assessed. So some notable applications of zero gravity that required an adaptation of the software and hardware of the machine are the AI-powered inspection of automotive plastic waste for recycling purposes, which you can see in the picture here on the left. We see a plastic part that is contaminated with a type of foam, and the AI model that we used, again, supervised learning, to detect this contamination. And so parts that are clean for foam can be recycled. And to do this inspection, here we have the image on the right. This system was modified. It had less cameras, and also the inside was blue to more easily detect these contaminants. And also the AI-based inspection of leather or footwear manufacturing that we saw before, both of these applications required some physical modifications to the design and structure of the machine, such as to cover very different methods of inspection. Now, as for future work, it is imperative that zero gravity is on constant improvement, and some new lines of work include using deep learning based models for surface inspection and fusing the results of these deep learning results into our 3D reconstructions. And we are also working on bettering the reconstruction of concavities of the piece that are currently not visible due to the camera layout, because we can see on the inside parts of the piece. And that was all. Thank you for listening to us. And now, if anyone has any questions, we would be glad to answer them.
Hi, everyone. I'm Silvia from the UPV, and Sainz Oscar had to leave the webinar. I'll take over this last part. So first of all, many thanks to Adriana and Nuria for this interesting presentation. And now it's the time to open the floor to questions from the audience. So if anyone has something to ask, just write your questions into the chat, okay? And in the meantime, I would like to start with a general question. And is that what are, in your opinion, the main technical challenges in achieving accurate 3D reconstructions with this multi-camera system, especially if we think in industrial environments?
I think I can answer it. Well, we have several challenges. In fact, to work in industry is always a very challenging environment, but we have mainly two or three challenges. The most difficult is very important to synchronize very well the cameras, because as the part is flying when we capture it, a small movement between different cameras on time synchronization will be very important at reconstructions. So the first time the first point is the camera synchronization, and also that we have to process a lot of information as we work with 16 cameras, and we have achieved a productivity of 1 part per second. We are able to process 60 parts per minute. It's a big amount of information that we must process very fast. So we have put a lot of efforts on algorithm optimization, and it's very important. And also we have working on create a distributed architecture of software that enable us to put more processes or more workers to process all this information. And finally, we have a product with a very high productivity that is able to reconstruct objects in 3D with very high accuracy, and that it's as we can see in these use cases that it's working very well in the industry.
Mm-hmm. Oh, that's clear. Thank you for the explanation.
You're welcome.
I think there is a question in the chat. Can you see the question? Nuria,
Yeah.
yeah.
What kind of objects or defect are hardest for our system to detect? So I think the type of pieces that mostly represent a challenge for our system are those that have very different and complicated textures, such as organic materials like wood or reflective specular surfaces. For these challenges, we have open lines of work, like I commented before. So, for example, for the organic material pieces, we are working on applying these state-of-the-art deep learning models to train these models to be able to inspect this type of materials that don't present a consistent pattern, such as like the knots in the wood. And for the specular surfaces like polished metal, glass, this type of materials act like mirrors, and it is a challenge to accurately inspect these objects' shape and surface. So for this type of challenge, what we are working on is a kind of ray tracing technique that would allow us to predict these reflections on the part, and that way identify any inconsistencies.
I don't know if anyone has something to ask. If you have, it's the time. It's everything clear. I don't know. So if there are no more questions, maybe we can finish here. Thank you everyone for joining us today, especially to our speakers. And we hope to see you next month in the final webinar of the project, which will be presented by Ikerlan. I think the day is the 17th on June. Yes. So thank you again, and have a great afternoon.
Thank you, Silvia.
Bye.
Have a good afternoon. Bye.